Hi guys, welcome back to another video. In today's video, we want to discuss densities. In the last video, we covered polar coordinates, and we've also covered rectangular coordinates for double integrals. That really covers all the formalism that we need. Now we're ready to apply it, and now because double integrals is able to deal with more nuanced situations than single integrals, we can expand our applications quite a bit. So one of the applications that we have is density. So there's a lot of physics that goes into the double integrals. So we can discuss density, we can discuss center of mass, moments of inertia, then we can discuss probabilities. There's really a lot that we can discuss, but first we want to start off with densities. It's a fairly easy subject. Now in the last course, we discussed how we can find densities of singular objects. So with a single integral, if I have an infinite plate, like that, maybe it's more dense over here, maybe it's more dense over here, maybe it's more dense over here, and then otherwise it's less dense. Well, then I can find the mass by integrating all the way across this thing with respect to x. I can integrate across my function, and then I can get my mass. Anyways, let's kind of cover a little bit of definitions, and we'll do an example. So the definition for density is that rho is what we call density. Rho is equal to mass over unit area or unit volume. Whatever kind of units you're dealing with, usually meters squared, meters cubed, whatever you like. So the idea is if you divide mass, so it's how much mass is in one standardized, normalized element of volume or area or space. Now, of course, we can expand on this to make rho a function of x and y. So if I have rho as a function of x and y, let's say I have some domain here. This is my object, and I want to describe the density of this. So what I do is I take a little area here, and then I determine its mass. Then I take a little area here, and I determine its mass. Then I make these areas a lot smaller, and then the end result will be a function that describes my density if I limit the difference in area and the difference in mass, and then divide that. Anyways, that's how we can get the density function. Now I would like to kind of expand on this. We can rearrange this equation. If I want to find the total mass, I can take the limit of the sum of rho of x and y delta A. So it weights my areas. It pretty much weights my little differential areas. Of course, that is equal to a double integral. So mass is equal to the double integral over whatever domain I'm working with of the density function with respect to area. Now, this also works for charge as well. If I have a plate and it is charged differently in different places, I might have a function called sigma that would tell me the charge density. So Q, the total charge, is equal to the integral over the charge density with respect to area. Okay, so let's try an example with charge density. This is from Stewart's book, problem 15.4.1. So let's say charge is distributed over a domain D, and the density is sigma equals x times y. Now D is going to be bounded by x equals 1, y equals 1, and y equals 1 minus x. We can draw that out. Here's our little graph. Here's x equals 1. Here's y equals 1. Here is y equals 1 minus x. There we go. And it intersects there. And so we want this region. I'm going to take this region so that we can define it. So it will be ordered pairs such that x is between 0 and 1, and y is between 1 minus x and 1. So now we're prepared to integrate over this. So we take q is equal to the integral over sigma with respect to area. And this can be rewritten as the integral between 0 and 1, and then the integral between 1 minus x and 1 of xy dy dx, which gives us the integral between 0 and 1 of 1/2 xy squared between 1 minus x and 1 with respect to x. We perform that theorem of calculus there, and then we get the integral between 0 and 1 of 1/2 x minus 1/2 x times 1 minus x squared dx. Now we can FOIL all of this and combine like terms, giving us the integral between 0 and 1 of x squared minus 1/2 x cubed dx. And if we evaluate that integral, which is fairly easy considering it is monomials, just apply the fundamental theorem of calculus, 0 terms cancel. We get Q is equal to 5/24 coulombs. So it's one of the first times we've used units in this course, but we do need to remember that we can use all of our formalisms for applied sciences or applied fields. All right, in the next video, I would like to discuss center of mass, and then we'll look at moment of inertia. A lot of great places to explore the applications of double integrals. Thanks for watching. We'll see you in the next one.